Hello everybody, this is Mikhail Polosan with probability lecture number 23. So today we're gonna continue our talk about random variables and talk about some important discrete random variables. We're gonna talk about discrete uniform distribution, Bernoulli binomial geometric distributions. But first let's give some reminder on random variables. Let's summarize what we have learned up to this point. So we have an experiment, probabilistic experiment, and the random variable x is a function over the sample space of that experiment, taking real values. So for each outcome, it is calculating some real number. In words, we are calculating some quantity for an outcome. And usually we are not interested in the outcomes of this experiment, we are not interested in the sample space, but rather we are interested in the quantity calculated for that outcome. And we are interested in the values of our random variable x. So we are forgetting about the experiment, the sample space, we are forgetting about outcomes and talking about possible values of x and probabilities of taking that values. Okay, and we have learned that we can describe any random variable completely in the sense that we can calculate all these kind of probabilities if we know the CDF, cumulative distribution function of that x. Also, we have learned that if we are dealing with discrete random variable, then we can describe that random variable also by using its PMF, probability mass function. We can calculate all these kind of probabilities, this type of probabilities, if we have the PMF, for discrete random variables. And also, for continuous random variables, we can calculate these probabilities if we have the PDF, probability density function, for that random variable. So, if we are dealing with discrete random variables, we can describe that random variables through their CDF or PMF, and if we are dealing with continuous random variables, we can give them through their PDF or again CDF. One note here, besides these three complete characteristics, besides CDF and probability density or mass function, there are also other complete characteristics, but unfortunately we are not covering, or fortunately maybe we are not covering that complete characteristics in our course. Two important complete characteristics are characteristic functions and moment generating functions. And people are using these characteristics, characteristic functions and moment generating functions, MGFs, for getting or proving some important results about random variables. For example, the central limit theorem, one of the important theorems in probability, which we will cover later, is proved by using characteristic functions. Okay. Now about discrete random variables. A random variable x is discrete if it is taking only finite or countably infinite many values. And if x1, x2, x3, etc. are all values of our x, and probabilities of taking the particular value xk is pk, so probabilities are written here, then this table is the PMF of our discrete random variable x. And having this PMF, we can calculate all probabilities concerning this random variable x. Now, another motivation for random variables. In the first part of our lecture, of our course, we're dealing with different probability problems, mostly of combinatorial and geometric types. And we have solved a lot of examples of this type. Say, this example is asking the following. We are rolling two fair dice independently, and we are asked to calculate the probability that we will have exactly two sixes. Or what is the probability that we will have exactly 1 6? Or what is the probability that we will have no 6s at all? Okay, if we will denote by NOS the number of 6s, then NOS will be a random variable with possible values 0, 1, 2. So NOS is equal to 0 means that we will have no 6s at all. NOS is equal to 1 means that we have exactly 1 6, etc. If we will complete this PMF table, if we will calculate these probabilities, or if we will have these probabilities, then we will have the solution of these 3 problems. So having the distribution PMF of our random variable means having the solution to these 3 problems simultaneously. Okay, and about the solution, so let's solve this problem. So the first part was to calculate, let's first calculate the probability that the number of 6s will be 2. So we need to write, because we are dealing with classical probability model with equiprobable outcomes, and our outcomes are all pairs of type ij, where I and j are running from 1 to 6 and the order matters. Then we have equiprobable case. Then the total number of cases is 36, so 36, and just one of them is favorable. The only favorable outcome is 6, 6, that pair 6, 6. So we have 2 6s, number of 6s is 2. So we have 1 over 36. Okay, and now to calculate the probability that the number of 6s will be exactly 1. So we can do the following. We can separate all possible cases giving with exactly 1 6. So we will have 1 6, then 2 6, then 3 6, then another outcome is 4 6, favorable outcome is 4 6, then 5 6. And now I'm not writing 6 6 because in that case the number of 6s will be 2, not exactly 1. And of course we need to add the cases when the first die was showing 6. So 6 1, 6 2, 6 2, 6 3, 6 4, and 6 5. All these outcomes are giving favorable ones. So this is our favorable event, and it is easy to calculate that we have exactly 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 favorable cases. So 10 over 36. Okay, now to calculate the probability that we will not have any 6s at all, we can do the following. We can use the following. Well, either we can write all possible favorable outcomes, or we can calculate in the following way. So number of 6s is 0, means first was not 6, and second was not 6. And this can be calculated. This can be calculated in the following way. So this is equal to, because we are dealing with independent case, so the first event and the second event are independent, and we have and here, we can write the product of probabilities. First is not 6, and second is not, well, not n, sorry. I need to erase this. So we will have product, so times probability that second is not 6. The probability that the first die is not showing 6 is 5 over 6. 5 favorables over 6 total, times the same for the second die, and we will have finally 25 over 36. So this probability is 25 over 36. Okay, let's move forward. And for the other solution, so this is solution number 2, we can visualize the sample space in the form of a table. So here is the result of first day. These are the results, possible results of second day. And say to calculate the probability of having exactly 2 sixes, number of sixes is exactly equal to 2, is only in this case we will have exactly 2 sixes, and this is 1 over the total number of outcomes, 36. Again, we are dealing with equiprobable case. And if we want to calculate the probability that number of sixes is equal to exactly 1, we can calculate in the following way. So let me take another color pencil. So we need to mark all pairs with exactly 1 6. So only this part, and only that part will work. Will give just 1 6. So we have 5 elements here, 5 elements here, and we will have 10 over, again, total 36. And if we are calculating, if we want to calculate the probability that we will not have any sixes at all, so number of sixes is equal to 0. This is this part, so we do not have any 6 here. Okay. This part. So you can calculate, we have 5 here, 5 here, so 25 elements, or 36 minus 10 minus 1. So this is giving 25 over 36. Okay, so if we will move forward, we can now fill this PMF table for our random variable NOS. So 0 with probability 25 over 36, 1 with probability 10 over 36, and I'm not cancelling, and here I have just 1 over 36. So this is the PMF of our random variable, and having this means that we can solve that problem with points A, B, C simultaneously. We have 10 here. Okay, so the idea of this example was that the distribution of our random variable is giving is solving several problems simultaneously. So we can calculate the probability of having 0 sixes, 1 sixes, or exactly 2 sixes simultaneously. Okay. Now we are forgetting about experiments and sample spaces behind. We are forgetting about outcomes. Sometimes, of course, I will give outcomes, but we are talking mostly about values of random variables and the probabilities of taking that values. Another example. So we have a random variable, discrete random variable, given through its PMF. So the values of x are -1, 1, 4, 6, and the corresponding probabilities are written here. By the way, the sum of all these four numbers is 1. So this is a legitimate PMF. So first, the problem is asking to plot the PMF by hand. This PMF by hand. Then the problem is asking to plot the PMF using R software. Then the problem is asking to give the frequentist interpretation for the PMF. I will give that. And then to do a computer experiment by generating 1000 values for x and calculating which percent of these values are equal to 4. So how many 4s we will have when generating 1000 times the values of x. So let's do let's solve this problem gradually. First, I want to draw the PMF by hand. This is easy. So we will have this kind of thing. So -1, 1, 4, 6. Let me open. So table was the following. These are the values of x, -1, 1, 4, and 6. 6 with probabilities 0.2, 0.1, 0.6, and 0.1 finally. So these are the probabilities of taking that values. Corresponding values. Okay. Now to draw the PMF, we need that Cartesian plane. This is x. This is the graph of our PMF, probability mass function. Okay. Now we have here on x-axis, I will mark the values of our x, and the y-axis will be for probabilities, for PMF values. Okay, so -1, -1, this is -1, then 1, then 4, then 6. Okay, and over -1, I'm taking a height, marking a point with height 0.2. So this is 0.2, 0.2. On 1, I'm taking 0.1. So this is 0.1, and this is that point. 0.6 here. So this is 0.6. And finally, 0.1 again over 6. So this is the graph of our PMF. Usually people are joining with this kind of lines, vertical lines. So let me try. Yeah. Okay. This is the PMF graph by hand. Now let's do that using R. So I'm erasing this, going back. Okay. This is our R. I'm opening a new R script to write here everything in, and then run, and then maybe save that file. So the values of our x are, sorry, I need to write in this way. So this is the same as to write x is equal to, and here I'm writing a vector. This vector will denote the vector of all possible values of our random variable x. So -1, then 1, then 4, then 6. I'm running that by hitting, when standing at that line, either Control and Enter or Alt Enter. So I'm hitting Control Enter. It is running and moving to the next line. So I have that render variable X now, not render variable, but variable X here. I need to input the vector of probabilities. So probabilities were 0.2, then 0.1, then 0.6, then again 0.1, and I'm running that. Okay, now I need to draw the PMF. So over the points X, I need to draw points with height 0.2, 0.1 P. So I'm just plot X, P versus X. So running this, sorry, yeah, I have something wrong here because I have 0, then 1, not 0.1. I need to write 0.1. Now I have that points. Over -1, I have 0.2, 0.1 over 1, and 4 points. Okay, people are usually writing this kind of thing, so I want to have horizontal lines. So the type of my plot is, I'm making that horizontal H. So I have lines with corresponding heights. And now I do not have that points, so I can add that points. I'm adding that points XP, the positions XP. So I'm running, I have that points. I can change the point type. Point character is equal to, say, 19, number 19. You can change this number and see what happens. So we have this kind of graph for our PMF. And finally, let me give a title to this graph. And the title is, say, our PMF. They're running this, and we have this kind of graph. You can zoom that. This is our PMF with heights, etc. And you can also export in PDF format or in image format, any image format. Okay, so the next problem was to give the frequentist interpretation for this random variable. What this random variable is meaning. Let me go back to our slides. So possible values of X are these 4. So if we will generate a value of X, if we will calculate, if we will observe the value of X, it will be either -1, 1, 4, or 6. Okay, if we will be able to generate a lot of times values of X, then most of the times we will have 4, because the probability of having 4 is 0.6. Then we will have -1s. Sometimes we will have 1 or 6. So the idea is the following. If we will have a lot of generation of values of X, a lot of experiments, repeat that again and again and again, then we will have 60% of times 4, around 60% of times 4, 10% of times 6, 10% of times 1, and 20% of times -1. This is the idea of the law of large numbers we will cover later. But now I want to give and describe the idea how you can understand or interpret random variables of this form. Okay, so now I will use R to generate 1000 or maybe more values for X, possible values for X, and then calculate how many of them are 4 and then percentage of that 4s in that 1000 values. Okay, so I'm moving to our R. So how to generate, how do that experiment? We have the vector x here, so we have the vector x. There is a function called sample in R. So you are giving x, you are giving how many times you want to do that experiment, that is size. You are giving whether to take with replacement or not, and you are giving the probabilities for each element. So here I'm writing x, so I'm sampling from this. The size is 1. I just want to do one experiment. So I will get either -1 or 1 or 4 or 6. Replacement, this is not important because we are just doing one experiment, but let me write that the replacement is true with replacement model. And then probabilities, I just want to have probabilities is equal to P with these probabilities. If I will skip this, then all probabilities will be the same. I will deal with equiprobable case. So I'm running this and I'm getting 4. Let me run that again. I'm getting 6. Let me run that again. I'm getting 4. Again 1, again 1, again 4, 4, -1, etc. So every time I will run, that will sample, that will give one possible value for x. Okay. Now the problem was asking to generate 1000 examples. Do that experiment 1000 times and calculate the value of x. I do not know which experiment is behind that random variable, but that is not important. I'm generating 1000 times the values of x with these corresponding probabilities. So number of experiment is, say, 1000 for me, and I'm doing 1000 experiments, so size is number of experiments. So I'm running this and I'm having 1000 elements with values -1, 1, 4, 6. You can see all values here. Okay, the problem was asking to calculate the percentage of force in this vector, in this sample. So let me keep this in some variable. Y is equal to that. In fact, I'm running this line second time, so the sample Y will not be the same. It is generating another sample. Okay, so how to calculate, how to find how many elements in Y are equal to 4. If I will write something like this, Y is equal to 4 with 2 equality signs. So in R, this is checking if the corresponding element of Y is 1000 dimensional vector consisting of these elements, and this will give either true or false. It will give true if the corresponding coordinate of our vector Y is equal to 4, and otherwise it will give false. So true if 4 is standing there, and false if not 4 is standing. So you can see that we have, true and falses, and the number of trues and falses is 1000 again. Now, if I will write something like this, choose from Y all elements with true coordinates here. So this is giving either false or true. If false is here, the corresponding coordinate of Y is not taken. If true is here, then the corresponding element is taken. So if I will write this, that will separate. Let me write Z is equal to separate all elements of Y which are 4. So I'm running this and z is a vector of size 604. So we have 604 fours. Okay, how to calculate that? I can calculate just the length of that vector. The length of that vector will give how many fours we have. So length of z, and I need to calculate the percentage. I'm dividing by number of experiments. So it is giving 0.604. So 60%, almost 60%, as we were expecting for fours. Let me run that again. The second time it will generate another sample, but hopefully the number will be close. So 595. Again, 593. Okay, if I will increase the number of experiments, say 100,000, let me select this. I'm selecting everything and running that again. Very close to 0.6. If I will change to, let me calculate how many minus ones I have when generating 100,000 elements with this distribution, then I will have almost 0.2. Okay. So going back to our example, so what this means, if we will generate a lot of values for x, if we will do that experiment again and again and again and calculate the values of x, then most of the time, almost 60% of times, we will have 4, and 10% of times we will have 6, etc. So this is one of the interpretation, and I wanted to show that to you. Okay, moving forward, and now we are starting our topic about important discrete univariate one-dimensional random variables. Later we will talk about two random variables, distribution of two random variables, and many random variables. Okay, starting from this lecture on, we will describe our random variables by giving its PMF. We will not describe by CDFs, but by PMFs for discrete case. And we will describe our random variables through their PDF for continuous case. And we will read or say that the distribution of our random variable x is given by this PDF or this PMF, or x is this kind of distributed. Say x is Bernoulli distributed, or x is normal distributed, or x is uniformly distributed, etc. And we will give some names to standard distributions. And we will write in this form the notation that x is a random variable with this distribution. So distribution name will be, say, geometric or uniform or other things. So usually our distributions will have some parameters, and we will include that parameters in distribution name. Say we will write x is x, this kind of notation, mark, and Bernoulli p, some equivalence sign, but this is not equivalence in probability. This is x is coming or is distributed like this. Okay, so if x is a Bernoulli random variable, if x has that distribution Bernoulli p, we will say that x is a Bernoulli random variable, or distribution of x is Bernoulli p, or x is a Bernoulli p distributed. So different types of reading this. Now, another notation. Assume x is a discrete random variable from our previous example, from the example 6. I do not know what is that example 6. And that is given, previous example, and that is given with this PMF. So this is the table. And we can write that. This is not common, but very useful to use. X is coming from this distribution. We are writing like a matrix. Here we have on the first row, we have the values, and on the second row we have the corresponding probabilities. So this is the same as writing that, but with this notation. One example, so x and y are this type distributed. So I'm giving the PMF, in fact, so give the distribution of x and y and check if x and y are discrete or not. So this is the same as to write x is, say, for x. X is taking the values minus 10 or 10 with probabilities. So these are probabilities. X is taking the value x, small x, small x, with probability 0.5 and 0.5. So this is the same as writing this. And the same for y. So I can add y here. Are x and y discrete? Of course they are discrete because they are taking just two values, minus 10 or 10. They can take only two values. Okay, the second part, what is the experiment behind x and y? Unfortunately, I cannot say what is the experiment behind x and y. And nobody can give what is the experiment behind x and y. Well, we can make some experiments. Say we are tossing a coin, fair coin. If heads, then say x is equal to minus 10. So I'm losing $10. Say. If tails happens, tails is shown, if tails is shown, then x is equal to 10. So I'm getting $10. What about y? Well, maybe y is equal to x, the same x. Or maybe y is equal to minus x. Or maybe y is completely different things defined on different experiment. Let me give another example. Say I'm picking a point at random from the interval 1, 3. So interval 1, 3. I'm picking a point at random from here. If my point is from 1 to 2, then y is equal to minus 10. If my point is between 2 and 3, then the value of y is 10. Again, I will have the same distribution, but completely on different experiment. So this notation, y is coming from this distribution or x is coming from this distribution, is saying what are possible values and what are the corresponding probabilities, but it is not saying anything about the experiment behind. That is not important in this case. So let me erase and move forward. Okay, so about distributions in R. There are a lot of distributions implemented in R, and they have some names. Say beta distributions name in R is beta, binomial distribution is binom, Cauchy distribution's name is Cauchy, etc. So we have a lot of numbers of distributions. Today we're going to talk about binomial distribution. So R's name will be binom. We're going to talk about geometric distribution. We're going to talk about Bernoulli distribution, which is a particular case of this binomial, and we will talk about the uniform distribution, which is not here. This is not that uniform. This is continuous uniform distribution. So today we're going to talk about discrete uniform distribution. Unfortunately, we will not cover all these distributions, but some part of that, say we're going to talk about this uniform distribution as an important example of a continuous distribution. We'll talk about normal distribution, we'll talk about Poisson distribution, etc. In statistics, you will learn about students' t distribution, which is very important. You will learn about chi-square distribution, etc. And how this probability names or distribution names are used in R. So for each name, this name is from previous table. R has 4 functions. So D and name, sorry, I need to erase this. D and with name. Say we can have D and binom. The name was binom for binomial distribution and D binom. Or P binom. We can have P binom. So what is giving D and the name of distribution, say D binom? It is calculating the P, D or MF. In this case, because binomial distribution is discrete, it will calculate PMF of that distribution. P binom will calculate the CDF of that distribution. Q binom will calculate the quantile of that distribution of corresponding order. So we have some parameters here, we need to put some parameters here, etc. Quantile, we will talk about quantiles, you will learn about quantiles in your statistics course. And R and the name of the distribution, say R binom is generating numbers, random numbers from binomial distribution. Our name is generating random numbers from that distribution with that name. Let me give some examples. I have here some examples, and later we will run in R and see the results, not now. So R norm is the name of that distribution. This is for normal distribution, very important, continuous distribution. We'll talk about that later. So R norm 10 is generating random numbers from normal distribution with some parameters. There are some default parameters here. 10 random numbers from normal distribution. D uniform, unif is the name of uniform distribution, continuous distribution. Sorry. D is for PDF in that case. So this is calculating the value of uniform distribution PDF at the point 1. So Px minus Px. Px at some point with some parameter minus Px at minus 3 with some parameter. So x is the name of exponential distribution, p is the name for CDF. So I'm calculating the CDF of exponential random variable at 3 with this parameter, then minus the CDF at minus 3. So in fact I'm calculating f3 minus f at minus 3. And this is giving, in fact, if you remember, the probability that our random variable x will be between minus 3 and 3, where x is an exponential random variable with this parameter rate is equal to 2. Later we will learn about this exponential distribution too. And the last one is q chi-square. So this is the name of that distribution, chi-square distribution, and q is calculating the quantile of that distribution of order 0.3. You will talk about quantiles and chi-square distribution in the statistics course. Okay, so let's move forward. Here I have something about the parameters of that random variable, about that distributions. All distributions have some parameters, and in R, the parameters have some default values. If we are not writing any values, then defaults are used. So, say for normal distribution has 2 parameters, the mean and standard deviation, and by default R is taking the mean is to be 0 and standard deviation to be 1. Okay, so our first discrete distribution, discrete uniform distribution. So the distribution name sorry, I need to close this. So distribution name is discrete uniform or discrete unif. We have n parameters here, x1, x2, xn, some points in R. So we say that our random variable has a discrete uniform distribution with these values or over these values if it is given through this PMF. So x is taking the values x1, x2, xn, x is taking these values with equal probabilities. So this is the equiprobable case. And we will write x is distributed like discrete unif x1, xn. This is not a common name, this is not a common distribution, but it is very useful. That's why I'm introducing this. Okay, so let me erase first. Move forward. So I can write the PMF in this function form, in this form. So the probability that x will take the value xk is 1 over n for any k. So these probabilities are equal to each other for different cases. So if x is discrete uniform over these values, then we can write that x is distributed like this. It is taking the values x1, x2, xn with probabilities 1 over n, etc. 1 over n. Now the usage, discrete uniform distribution models equiprobable outcomes case, and we have talked about a lot of examples of equiprobable type. Some examples are, say, we are tossing a fair coin, x is 0 if heads appears, and x is 1 in the other case. So in this case, we can write that x is, so the distribution of x will be, so it is taking two values, 0 and 1. It is taking the value 0 if heads appears. And so the probability of 0 is when we will have heads, so the probability of heads is 1 over 2. And the probability of tails is again 1 over 2. So this is the case when probabilities are equal, equiprobable case. So we can write in another way, discrete, uniform, taking the values only 0 and 1. So let me write in this way, 0 and 1. So for discrete uniform case, we do not need to specify the probabilities because in this case, when giving this name, we know that all probabilities are the same. And because their sum need to be 1, we can calculate that probabilities, of course. Let me erase this, move forward. So x will be discrete uniform with values 0, 1. And this is meaning that the PMF is this 0, 1 with probabilities 1 over 2, 1 over 2, and here I have the probability that x is taking that particular value of small x, and small x can be 0 or 1. Okay. The next example is we are rolling a fair die. X is the number shown on the top face. Then, of course, x is discrete uniform with values 1, 2, 3, 4, 5, 6. That is, we will have this PMF. So the values are written here and probabilities are written here. Probabilities are all equal to each other because we are talking about discrete uniform case. And you can give a lot of examples of this type. Try to give some. Now, an example. We are given that x is discrete uniform over these values. And the A part is to calculate this probability. The probability that x is taking the value 4. So let me first write what this means. Let me write in the PMF form. So x is taking these values, minus 1, 0, 4, or 5, with equal probabilities, because we are talking about uniform, discrete uniform distribution. So because we have 4 elements, I will have 1 over 4, 1 over 4, 1 over 4, and 1 over 4. So this is some notation for this, the same as this. Again, we are asked to calculate the probability that x is taking the value 4. So x is taking the value 4 with this probability. So this is equal to 1 over 4. Now, calculate the probability that x will be larger or equal than 0. So x will be either 0 or 4 or 5. Well, either we can add this 1 over 4 plus 1 over 4 plus 1 over 4, or we can write, and I want to write it in this way. So this is the probability that 1 minus the probability that x will be less than 0, taking the complement. And this is equal to the probability that x will be less than 0 is the same as the probability that x will take the value minus 1. The only value of x which is less than 0 is minus 1. So that probability is 1 over 4. So 1 minus 1 over 4, which is again 3 over 4. Okay. And here I have an R code for discrete uniform distribution, generating a sample from that distribution. Let me pass to R and solve a problem for you. So I'm selecting everything, removing. Now I need to make a vector of values. I want to have, say, discrete uniform over the values minus 3, 1, 4, 7. So my random variable will take values minus 3, 1, 4, 7 with equal probabilities. So either I can write the probabilities here, or I can skip that and just write sample from x. How many elements, sorry, size, not same, size. How many elements I want to have? Just make one experiment for me. Take one of the elements here and replaces, say, for size 1, replacement true is not so important, or false is not important. So if I will run this, that will give, so this is the value, that will give one possible, no, this is not correct. I cannot have 6 when generating from that. This is because I forgot to run this. Okay, now I have new x, and now if I will generate a sample of size 1, I will have 1. So I'm doing once that experiment, I'm observing a value of x. Now let me observe 10 values, say 10 times do that experiment and generate results as a vector, in a vector form. So if I will run this, that will generate 4, 7, 1, 4, 7, minus 3. So values from these possible values are minus 3, 1, 4, 7. Okay, because I'm not specifying the probabilities, there is another parameter here. Sorry, if I will write something like that, probabilities. If I'm not specifying probabilities, then by default, I have equal probabilities. So I'm not specifying, I have discrete uniform case. Okay, let's go back. The next one is Bernoulli distribution. So, important distribution. The name of distribution is Bernoulli, and it has a parameter P. P is a probability, so P is between 0 and 1, any number between 0 and 1. We say that X is Bernoulli distributed with parameter P, and we will write like this, so let me mark that. So we will read this as the distribution of X is Bernoulli P, or x is Bernoulli P random variable, and the definition is the following. X is Bernoulli P if the values of x are 0 or 1 with the following probability. So the probability of 1 is P, and the probability of 0 is 1 minus P. So if I will move forward, you will see in this form, so probability that x is taking 1 is P, and the probability that x is taking 0 is 1 minus P. By the way, it is important to have the probability P here, not there. So I'm not writing, let me erase this, I'm not writing 0 with probability P and 1 with probability 1 minus P. Why is that? Because usually we interpret this one as success, and we are interpreting 0 as failure. So we want to have that probability. This is called the probability of success of 1, the probability of 1. So let's move forward. So x is Bernoulli random variable with probability P or with parameter P if it has this PMF. This is important for statistics. The PMF, this can be written in this form. So if P is between 0 and 1, not including 0 and 1, then the PMF can be written in the following way. And x is taking only two values, 0 and 1. X is taking the values 0 and 1. How to check this? Say I'm plugging 0 here. If x is 0 here, then I need to take 0 here and 0 here. And in that case, I will have p to the 0, and this will give 1. And I will have 1 minus p to 1, and this will give 1 minus p. So if x is 0, I will have this 1 minus p. If I plug instead x is 1, so 1 here for x, I will have 1 here, and I will have 1 here. I will have p here, and this will give 0, and this will give 1. The power is 0, so 1 minus p to the 0 will give 1. So this will give p. And if x is 1, then this is p. So this functional form of that PMF you will use in statistics. Okay, we already learned that we are usually decoding this one as a success and the 0 is a failure. So P is the probability of success. Usage of Bernoulli distribution. There are a lot of examples of Bernoulli distribution. Bernoulli distribution models binary outcomes case. So success failure types case. Say yes, no types of problems. Boy, girl, pass, fail, healthy or ill, smoker, non-smoker, etc. These kind of examples are modeled by Bernoulli distribution, and I will give a lot of examples of that type, and you can continue by giving a lot more. We are tossing a fair coin. If heads appears, then x is 0. If tails appears, x is 1. Then x is Bernoulli 1/2. Of course, this was the same as discrete uniform. Let me write du for short. 0, 1 over 0, 1. But also, x is Bernoulli 1/2. So that means that x can take the value 0 or 1 with probability. This is p. I'm starting from this 1/2 and 1/2 here. So this is the distribution of our random variable x for these experiments, for heads and tails experiments, for fair coin. Okay, moving forward, we are rolling a fair die. So fair die, x is 0 if the shown number is larger than 4, and x is 1 otherwise. So x is Bernoulli with some parameters. Why is Bernoulli? Because x is taking only values 0 and 1. So x is taking values 0 or 1. So let's see with which probability. The probability of having 1. So this is our p. So x is taking the value 1. Otherwise, if the shown number is less or equal than 4, and we have 4 possibilities in 6 total. So we can have either 1, 2, 3, or 4 among that 6 possibilities. So this will be 4 over 6 or 2 over 3. And here we will have 1 minus this. So 1 minus that is 2 over 6, which is 1 over 3. So here I need to write this p, this number, which is of course 2 over 3. So for this random variable in our experiment of rolling a die, the distribution of x will be Bernoulli 2 over 3. This is an indicator in some sense of whether that number shown will be larger than 4 or not. If it is larger, then the value is 1. If it is smaller or equal than 4, the value is 1. Otherwise, it is 0. So indicator function. Okay, so let's move forward. Another example is choosing a probability student at random in AUA, and we will denote by 1. So this is our outcome. We are choosing, this is our experiment, sorry. Experiment is choosing a random probability student in AUA. And outcome will be one of students, probability students in AUA. We denote by x is equal to 1. In the case the student will pass the course, and x is 0 otherwise. So if that student will pass the course, we will write x is equal to 1, otherwise x is equal to 0. So this is a random variable. We do not know beforehand what will be the value of x. Say we can model x through our historical data, say 76% of students are passing the course, then I can model that and say that x is Bernoulli 0.76, meaning that x will take the value 0 and 1 with probability 0.76 and 1 minus 0.76, which is 0.24. So the chances that that student will pass the course is 76%, and the probability of failure is 0.24%. We are interested if a randomly chosen probability student will get the grade A. Again, the same experiment, but now I'm interested in another random variable. So x is 1 if that person, that student, will get A, otherwise it is 0. Then x is Bernoulli p. Hopefully this p is large, so probability of getting A is large in our course. And how to calculate this p? Well, this is about statistics. Statistics will give tools to calculate that probability p. In fact, we can take historical data, calculate how many students I have, well, how many probability students were in AUA and how many of them were A students, A grade students, and calculate the ratio of that A grade students among all probability students in AUA we had so far. Okay. Another example, we are interested if a patient has a specific disease or not. X is 1 means he or she has that disease, X is 0 otherwise, and in this case P will be the probability of having disease, the probability of this. Of course, in this case, talking about success is not correct, but this is a term, general term for Bernoulli random variable. Next example, we are interested if the nearest toilet, I'm skipping this example, you can read that by yourself. An insurance company is interested if the claim size for today will exceed 10 million Armenian drams. So x is 1 if it will exceed and 0 otherwise. And x will be a Bernoulli random variable where p is the probability of exceeding that claim size exceeding 10 millions. Another example, we are interested if the maximum of stock price for Facebook stock next month will be higher than the maximum stock price today. So today the maximum stock price will be something or is something, and we are interested if the next month's maximum price will be higher. If it will be higher, then x is 1. Our random variable is showing if it is higher or not. And our random variable, that x random variable, will be a Bernoulli random variable with some parameter p, with some probability p. Okay, another example is we are interested if some specific football team will win the next game. X is 1 means it will win, and x is 0 means they will lose. So x is Bernoulli p, and p is the probability of winning for that football team. Or with the same experiment, again the same football team, we are interested if that team will win with the next game with the difference in scores more than 3. So x is 1 if that will be case, so if the difference in scores will be more than 3, and 0 otherwise. And p is the probability here that that team will win with difference in scores more than 3. And you can give a lot of examples of this type of Bernoulli random variables. Another interpretation of Bernoulli random variable is that it is an indicator random variable. I was talking about that. So the general idea is the following. So we have an experiment and an event A in that experiment. P is the probability of that experiment, in that experiment. And if A happens, then x is 1. Otherwise, x is 0. In that case, we will have something like this, 0, 1. So 1 if A happens, and 0 if not A happens. And the probability of A happening is P, and not A probability is 1 minus P. So we will have this the same as Bernoulli P. Okay. So we can think about Bernoulli random variable as an indicator random variable. Let's move forward. So an example, assume x is Bernoulli 0.2 with parameter 0.2. We need to calculate the probability that x will be between 0.1 and 0.7, and we need to calculate the probability that x will be between 0.7 and square root of 2. Okay, so what this means? This means that x is taking two values, only 0 and 1, because it is Bernoulli, and the probability of 1 is 0.2, and the probability of 0 is 0.8. And this is all what this is meaning. Okay, so we need to calculate the probability that x is between 0.1 and 0.7. Okay, x is taking only two values, 0 and 1, and none of them is between these. So the probability that x will take values between 0.1 and 0.7 is 0 just. And the probability that x will take values between 0.7 and square root of 2 approximately is 1.4. So only one value is there. So this is the same as to write this is the probability that x is equal to 1. And the probability that x is equal to 1 is 0.2. Okay, let's move forward. This is the R code to generate random numbers from Bernoulli distribution. In fact, we are writing binom, but if in binom, we will talk about binomial distribution next. If the size of binomial distribution is 1, then we have Bernoulli distribution. So let me do that experiment for you. So we are moving to R. So the distribution name was, we are generating Bernoulli, but the name was binom. So we need to write R binom because we want to generate random numbers. So R binom, N is how many experiments we want to do. N is equal to 1. Just once do that experiment. And size is equal, well, if we want to have Bernoulli, we need to take size 1. And probabilities, by the way, when standing here, how I'm opening this menu, I'm just hitting tab, standing there. So probabilities, this is the probability of success of 1. And this is, say, I'm taking 0.7. So what this means? So I'm doing Bernoulli experiment. The probability of success is 0.7. So Bernoulli experiment means I can have either 0 or 1 for my random variable. So this will give just one number, either 0 or 1. With high probability, with probability 0.7, it will be 1 or it will be 0. Let me run that once. It is 1. Again, 0, 1, 1, 1, 0, 1, 1, 0. So sometimes it is giving more ones than zeros. So if I will ask to do that experiment 10 times, so this is giving how many times you want to do that experiment, the general results. So this will give 10 elements. So it is doing that experiment, repeating that experiment, and all times we have once. I'm doing that again. Sometimes we have ones, sometimes zeros. By the way, 7, exactly 7 ones and 3 zeros. And I'm doing that again. Sometimes zeros, sometimes ones. Again. So you can see that we have 4 zeros here and 6 ones. So R can do that experiment for you and generate values for random variables.